Positive semi-definite matrices are square matrices that have many special properties. They arise all over the place in machine learning. So today we'll see what it means for a matrix to be positive semi-definite, and we'll look at some of the properties of these matrices. We'll also cover the important question of how you figure out if a matrix is of this type. Now, when we were talking about convexity, we said that a function of one variable is convex if its second derivative is always positive. When you have a function of d variables, however, the second derivative is a d by d matrix. What might it mean for a d by d square matrix to be positive? How could we define that? Well, one natural notion is to say that a matrix is positive if all the entries in it are positive. This is reasonable enough, but it turns out to be a superficial notion that doesn't really help us very much. There's a deeper and more insightful notion. We can say that a matrix, a square matrix, is positive if the quadratic function defined by it is always positive. Let's see what this might mean. Okay, so here's a matrix. What is the quadratic function defined by this matrix? Well, if you recall, the quadratic function defined by this matrix is the function that maps a vector x to x transpose mx. So in this particular example, x has to be a two-dimensional vector, okay? And the quadratic function sends this vector, say x1, x2, to x transpose, so x1, x2, times m, 1, 1, 1, 1, times x, x1, x2. What is that? Well, let's work it out. Let's start by doing this. Okay, so we get x1, x2, and here we get x1 plus x2, x1 plus x2. And now we do the last product and we get x1 squared plus 2 x1 x2 plus x2 squared. This is the quadratic function defined by the matrix. Okay? Now if you look at that function, you can see that it can also be written like this, x1 plus x2 squared. And when you write it like that, it's a square, which means that it always has to be greater than or equal to 0, no matter what x you plug in. Okay? So we have a matrix, in this case 2 by 2. It defines a quadratic function on two variables, and this function is always greater than or equal to 0, no matter what x you plug in. So we call this matrix M positive semi-definite. More generally, let's say we have a d by d square matrix. Okay. In that case, the quadratic function defined by the matrix is this one, that sends a d-dimensional vector x to x transpose mx. So what exactly is x transpose mx? Well, it works out to a number. And if you multiply it out, you'll see that it's actually just this summation. It's the sum over all ij of the ij entry of the matrix times the ith entry of x times the jth entry of x. And if you add all those things up, that's x transpose mx. So we'll say that a matrix M is positive semi-definite if, first of all, it is symmetric, and second, if this quadratic function, x transpose mx, is always greater than or equal to 0, no matter what x you plug in. This turns out to be a very powerful notion of what it means for a matrix to be positive. So let's look at an example. Okay, so we've seen that this matrix is positive semi-definite. We just worked through that example. What about this other matrix over here? Is that positive semi-definite as well? Well, it's a 2 by 2 matrix, so the quadratic function is the one that sends x1, x2 to x transpose mx, And if we just plug into our usual expansion, this would be, it would send this to x1 squared plus 4x1 x2 plus x2 squared. That's the quadratic function given by the matrix. So is this always greater than or equal to 0? You know what? Let's try some values. What about trying x1 equals 1 and x2 equals minus 1? What happens then? In that case, we get 1 minus 4 plus 1, which is negative 2. Okay, so this matrix is not positive semi-definite. And yet, it looks more positive than the other matrix, which we know is positive semi-definite. Here's another question. Suppose we have a diagonal matrix. Under what conditions is it positive semi-definite? Okay, so we have some diagonal matrix. So the diagonal entries are M11, M22, all the way to MDD. And everything else is a 0. When is a matrix like this positive semi-definite? Well, we know x transpose mx has to be greater than or equal to 0. Why don't we try this x? Let's try the vector x, which is 0 everywhere except for a 1 at the ith position. Okay, so it's all zeros except for a 1 at the ith position. What is x transpose mx? Well, if we think of our summation, the sum of mij, xi, xj, you can see that x transpose mx is just the ii entry of the matrix. And so we know that this has to be greater than or equal to 0. Okay, so that gives us a simple condition. A diagonal matrix is positive semi-definite if and only if all the diagonal entries are greater than or equal to 0. So for diagonal matrices, it's very easy to check. Okay. Now suppose we have a positive semi-definite matrix M. What about 2 times M? Is that positive semi-definite as well? Yes, it is. And more generally, what about C times M? Well, let's take a look. So we have x transpose C times M x. C is just a constant, so we can pull it out. So it's C times x transpose mx. And M is positive semi-definite. So this is greater than or equal to 0. C times that, is that greater than or equal to 0? Yes, provided C is greater than or equal to 0. Okay. So the answer is yes, if C is greater than or equal to 0. Here's a related question. Suppose you have 2 matrices that are each positive semi-definite. What about their sum? Is that positive semi-definite? Well, again, we can just try directly by plugging into the definition. Let's take their sum, m plus n, and look at x transpose m plus n x. Now we can factor this. This is just equal to x transpose mx plus x transpose nx. And each of these are greater than or equal to 0. So the whole thing is greater than or equal to 0. And so the answer to this question is just a simple yes. Okay, so we've seen many properties of positive semi-definite matrices. But the thing that we're going to have to do pretty often is to figure out whether a given matrix is positive semi-definite. Now technically that means that we have to check if x transpose mx is greater than or equal to 0 for all x. That's difficult to do because there are infinitely many choices for x. Is there a simple way? Is there some more direct way of checking whether a matrix is positive semi-definite? And indeed there is. There's a very simple condition. It's positive semi-definite if it's of the form UU transpose. So let's just briefly go over the justification for this. So let's say that M is of this form, U transpose, and U is just any old matrix. Let's say it's an R by D matrix, okay? And let's just go and check all the properties for positive semi-definite. So first of all, is M even a square matrix? Well, let's see. M is U transpose. U is R by D, and U transpose is D by R, so M is an R by R matrix. Yes, it's square. Okay, we're off to a good start. Now, is M symmetric? Okay, let's see. Well, U transpose, what's the transpose of that? What is that equal to? Well, if you remember, we had this formula for transpose. AB transpose is B transpose A transpose. So if we apply that, we get U transpose transpose times U transpose. What is transpose transpose? Well, if you just transpose a matrix twice, you get back the same matrix. So that's just U transpose. And yes, M transpose equals M, so it is symmetric. Okay, so just one last property to check. Okay, so X transpose MX, we plug in U transpose for M. And now we have this matrix vector product involving 4 terms. We can just parenthesize this however we like. So let's do it like this. Let's put the parentheses there. Okay, and let's look at these terms. Now, X transpose U. By again using this transpose formula, we can just write that as U transpose X transposed. And now U transpose X is just a vector, and so we get something of the form vector transpose with itself. That's familiar. If you remember, Z transpose Z is just the length of Z squared. Okay? So U transpose X transposed times U transpose X is just the length of U transpose X squared. And since it's the squared length, it has to be greater than or equal to 0. And so a matrix of this form has to be positive semi-definite. This will turn out to be a very useful rule. Okay? Now, essentially the same argument can be used to show something else that will be useful, which is that any covariance matrix is guaranteed to be positive semi-definite. So here's a picture that I would like to leave you with. We're talking about square matrices, say D by D matrices. Some of these matrices are symmetric, that is, M equals M transpose. This is a special property. An even more special case is when the quadratic function defined by the matrix, X transpose MX, is always greater than or equal to 0, no matter what X you plug in. These are the positive semi-definite matrices. They arise all the time in machine learning, and we rely upon them very heavily in many different contexts. Okay, that's enough for today. We've finally seen what it means for a matrix to be positive semi-definite, and we've already seen one use of these matrices in deciding whether a function is convex. We'll soon see many more uses. See you soon.